Okay, let's dive into this. Welcome to today's explainer. We're going to be demystifying one of the most foundational, but honestly, absolutely fascinating concepts in all of machine learning. And the crazy thing is, you and I interact with this tech literally every single day, usually without even realizing it's happening. I mean, think about it for a second. How does your inbox actually know what's spam and what's a super crucial message from your boss? Well, spoiler alert, it is definitely not magic. Right behind the scenes, there is a machine learning classification model just working tirelessly to make that exact distinction. So today, we're going to pull back the curtain. We'll see exactly how that decision gets made, and honestly, more importantly, how we measure if that decision was actually any good to begin with. So, here is our roadmap for the explainer. First, we'll look at the classification problem itself. Then, we'll talk about drawing the threshold line, step inside the confusion matrix, break down precision, recall, and accuracy, and then finally, we'll zoom out for the big picture evaluation. Let's get right to it. Number 1, the classification problem. When data scientists talk about classification, what they're really talking about is just predicting which category a specific example belongs to. Is this spam or not spam? Is this tumor malignant or benign? But here's the kicker. Machine learning models don't just naturally spit out a firm yes or no. It's not that simple. Instead, they output a probability. So, for instance, a model might look at an incoming email and give it a score of 0.99. What that means is the model has a 99% confidence that this specific email belongs to the positive class, which in our case means it's spam. So yeah, that is a really confident prediction. Now contrast that with a score of, say, 0.51. At 51% confidence, the model is essentially just shrugging its shoulders at you. And this tells us something super important. The reality is that model predictions are not these neatly separated boxes. They are a messy continuum of floating point numbers just scattered all across the line between 0 and 1. Which brings us to part 2, drawing the threshold line. Because at the end of the day, your email inbox can't just hand you an email and say, hey, this is 51% spam. It has to make a firm choice. It either drops it in your main inbox or it banishes it to the spam folder. There is no in-between. So the crucial point here is that we, meaning the humans actually designing the system, we have to tell the model exactly where to draw that line. We set what's called a classification threshold. If we set that threshold right at 0.5, then anything 0.5 and above gets labeled as spam, and anything below is not spam. Seems completely logical, right? Well, as you'll see in a minute, 0.5 isn't always the smartest choice. And that is because our predictions are this messy continuum we just talked about. Setting a firm threshold is inevitably going to create mistakes. So let's move to section 3, inside the confusion matrix. We really need to see exactly what those mistakes look like. Okay, take a look at this. Notice how every single possible outcome of our model's decisions breaks down into this tidy 4-box grid. When reality and our prediction perfectly match, we get a true positive, like spam actually caught in the spam folder, or a true negative, a real email sitting safely in your inbox. But look at the cross sections. This is where it gets tricky. A false positive means a completely legitimate, maybe even vital email was misclassified and thrown into your spam folder. And a false negative? That means a piece of junk spam slipped right past the filter and landed straight in your main inbox. Ultimately, our big goal when we're tuning our machine learning model is to maximize those true boxes and shrink the false boxes as much as we humanly can. But as you've probably guessed by now, there is always a trade-off. So section 4, precision, recall, and accuracy. How in the world do we actually mathematically measure those mistakes? And this brilliantly illustrates the real tension right at the heart of machine learning classification. Let's look at precision first. Precision asks, when the model cried wolf, was there actually a wolf? If you want to absolutely guarantee that a legitimate email never ever goes to spam, you want high precision. Recall, on the flip side, asks, out of all the real wolves out there, how many did we actually catch? If you want to make sure 0 spam ever gets through, you want high recall. But here is the catch. Improving one almost always worsens the other. If you lower your threshold to catch more spam, you are inevitably going to flag more real emails by accident. It's a total balancing act. Let's actually apply this to a real-world scenario. Imagine you have a camera trap system set up out in the wild to detect a highly dangerous invasive insect. Now, 99% of the time, the photos it takes are just totally normal local bugs. Only 1% of the time is it actually the dangerous species. In data science, this is what we call an imbalanced data set. So I really want you to think about this question for a second. If your data set is 99% normal, is getting 99% accuracy actually a success? Well, believe it or not, the answer is no. Think about it. If I build a completely broken model that just blindly guesses normal on every single photo it sees, it's going to be right 99% of the time. It literally has 99% accuracy, but it completely missed every single invasive insect, which makes it, well, utterly useless. This is exactly why we have to choose our metrics based on the real-world cost of a mistake. In our insect example, missing the invasive species is hugely costly, right? It could literally cause a devastating infestation. A false alarm, though? That just means some entomologist wastes like 5 seconds looking at a blurry photo of a moth. Therefore, in that specific case, we must prioritize recall. But if a false alarm means a business-critical email gets completely blocked, then we have to prioritize precision. Accuracy, well, accuracy is really only a reliable indicator when your data set is perfectly balanced to begin with. So, if changing the threshold completely changes our precision and recall, how do developers evaluate a model overall? Let's get into Section 5, the big picture evaluation. To see that big picture, we use something called an ROC curve. And here's a fun fact for you. The name Receiver Operating Characteristic actually comes from radar detection back in World War II. An ROC curve graphs the true positive rate against the false positive rate across every single possible threshold. This is incredibly useful because it lets developers evaluate the fundamental quality of the model without having to commit to just one specific threshold line right out of the gate. And to actually quantify that ROC curve, we calculate the AUC, or area under the curve. This gives us a single, neat number. An AUC of 1.0, that means it's a perfect model. It'll always rank a randomly chosen positive example higher than a randomly chosen negative one. But an AUC of 0.5, well, on the graph, that's just a flat diagonal line. It basically means your incredibly complex machine learning model is doing the exact same thing as just flipping a coin. By looking at this ROC curve, a developer can literally slide up and down the line to pick the absolute perfect threshold for their specific needs. They can choose a point that lowers the false positive rate if false alarms are disastrous. They can maximize the true positive rate if misses are disastrous. Or they can just find a sweet spot right in the middle if the cost of those mistakes are roughly equivalent. And as a quick sanity check, developers will also look at something called prediction bias. It's wonderfully simple. If your training data is, say, 5% spam, your model should, on average, predict that 5% of things are spam. If it's suddenly predicting 50%, you immediately know something is fundamentally wrong. It could be your data, your features, or your model pipeline, but something is broken.
Now, everything we've talked about so far today has been binary. Spam or not spam, yes or no. But it is definitely worth noting that if you want to sort things into many categories, like, say, a system reading handwritten digits from 0 to 9, you just stack these binary classifications together, basically asking, is it a 0 or not? Okay, is it a 1 or not? The exact same foundational rules we just learned still apply.
Which brings us to our absolute most important takeaway from this whole explainer. Machine learning can so often seem like this cold, purely objective mathematics. But choosing that threshold, choosing whether you're going to prioritize precision or recall, that is entirely a human judgment call. It requires developers to actually look at the real-world impact and decide exactly what kinds of mistakes they are willing to live with. Because at the end of the day, AI is not flawless magic. It's a system of calculated, human-designed, probabilistic bets. So I'm going to leave you with this thought. The next time an important email goes straight to your spam folder, or an algorithm recommends a video to you, or an AI system flags one of your transactions, ask yourself, what kind of mistake was its creator willing to live with? Thanks so much for joining me for this explainer, and keep learning.